go.
All right, I'll begin with the prayer.
Very good.
Lord, thank you for this day. Please help us today as we try to understand this material. Amen.
Amen.
Nope. Pretty sweet.
Golly.
All right, so today we're going over Chapter 5 in Rotman, which is long exact sequences. A lot of what we're going to be doing, especially towards the beginning of the chapter, which is probably all we're going to get the chance to cover today, is in a lot of ways just an extension of what we did last chapter. Whereas last chapter we talked about things from the perspective of individual homology groups. Here we're going to be sort of lifting a lot of those definitions to chain complexes. So you've already seen a bit of this in chapter 4 with the singular complexes. But in general, a chain complex is a sequence of abelian groups and homomorphisms, like so, indexed by the integers, with these homomorphisms here that are called differentiation of degree n, such that essentially d squared is equal to 0 for all n. So the singular complex from chapter 4, of course, is an example of this.
Right.
And as we continue on, we'll see a lot more examples. They also note that this condition here is equivalent to saying that the image of the n+1 differentiation is contained in the kernel of the nth differentiation. So let me have another definition. So a sequence of two homomorphisms group homomorphisms, of course, so let's call them F and G, is exact at B if the image of F is equal to the kernel of G. So of course, if we have...
Oh, I was thinking this was a short exact sequence, but that's addressed in exercise 5.3.
Right.
There's zeros before and after. Yeah.
So, of course, if you have this exactness condition at each of the groups in a sequence like this, image is going to be equal to the kernel of the next homomorphism up in the sequence. So obviously you'll get this condition. So this is a stronger condition than just being a chain complex. So a few of these exercises here, like you were just mentioning, are useful.
Stronger condition in the chain complex in what sense did you say?
Well, if you have just a sequence of homomorphisms and abelian groups like this, and it's exact at each of the groups, then you'll have a chain complex.
Oh.
Because if the image of your nth homomorphism is equal to the kernel of your n+1, that obviously implies that it's contained in the kernel of the... I think I had that backwards, but you get what I was saying. I want to think that it's increasing, but with homology groups it's decreasing when you go to the right. So these exercises here, I'll just read them because it's a lot of writing. Well, I should probably write them. So if you have 0, A, B is exact, this of course just being the trivial homomorphism, which is the only possibility. If this is exact, then F must be injective, right? Because the image of the trivial group is just 0, and by our exactness condition, the kernel of F has to be 0, which implies F is injective. So that's pretty simple. Similarly, if you have something like this, B, C, 0. Yeah, there's some morphisms G. And this is exact. Then G is surjective. Since, let's see here, the kernel of this map is going to be all of C. So that means the image of G has to be all of C as well, which means that it's surjective. And so from that you can see if you have these two things combined, right? So if you have a sequence like 0, A, B, C, 0, that's exact. And you have, oh wait, hang on. Yeah, I guess this is just F.
Okay.
Then this must be an isomorphism,
Isomorphism.
because by this being exact, that tells you that it's injective, and by this being exact, that tells you that it's surjective.
Mm-hmm.
So the rest of those are useful as well, but I'll just move on
Okay.
because we don't have a ton of time. So our next definition,
Oh, I'm sorry.
let's see. Like I was saying, we're doing essentially some of the same definitions that we did before, but we're moving them to the level of complexes. So, definition, if S star partial is a complex, then the kernel partial n is the group of n cycles, and similarly, oh, and it's denoted Z n S star comma partial, and then similarly the image of the n+1 differentiation map is the group of n boundaries. And is denoted B sub n so then we define the nth homology group of the complex is Hn.
I guess the main difference here is that we're doing it for an arbitrary chain complex right now. It's
Right,
an
exactly.
algebra discussion as opposed to last chapter, which was specifically about homology.
Right, what we're going to
Yeah.
see in a second here is essentially this framework lets us break up the homology functor construction into a step where you convert topological structure into a chain complex, which is the topological step essentially.
Mm-hmm.
Then you take your chain complex and you convert it into an abelian group. So essentially we're just giving a bit more detail to what we've already done and generalizing it somewhat.
It's sort of the linear algebra to the problem.
Yeah. So this defined as before, although of course, like we were just saying, this is slightly more general.
Sure. Okay.
We take the cycle's Mach boundaries.
Okay, so then...
So, and again, we use the same notation as before.
Oh man, this stuff is pretty.
We use CLS for the class of Zn.
Right.
So, theorem. This is 5.1.
This one I think I could do.
Yeah. A complex
Sorry.
is an exact sequence if and only if the nth homology group of the complex is equal to 0 for all n. And proof only every proof in this chapter was like this one. That'd be nice. Unfortunately, is not the case. Zn is equal to Bn if and only if the kernel of the nth differentiation map is equal to image of the n plus 1.
So their quotient is 0.
Yep. Alright, so you notice the subheading here is the category comp. Chain complexes actually form a category. So that's our next definition here. We define the morphisms of that category, which are chain maps. So move over here. Definition. See. So another thing I didn't like about this section, he uses a lot of primes. Kind of makes things annoying to look at, but I guess I'll use the same notation as him. So if S star prime, partial prime, and S star partial are complexes, then a chain map F from one complex to the other is a sequence of homomorphisms Fn from the, I think I forgot to mention the actual groups in the chain are called, what was it? The term of degree n. So these are, a chain map consists of a sequence of these homomorphisms from the nth term of the complex to the nth term of the other complex, such that following graph commutes. So essentially, you just line each of the terms up. And these are your homomorphisms.
Term of degree n.
Right.
Yeah.
This one.
Should call this thing like a ladder or something,
so,
you know?
Yeah.
Or a ribbon, or I don't know.
So then this has to commute. And in particular, typically how we're going to make use of this entire diagram commuting is the fact that I forgot to write the differentiation. That's important.
Yeah.
I guess this partial.
Well, you said you said the diagram commuted. Oh, you have to add the.
Yeah.
You say the diagram commuted, but there's nothing on the diagram. I got you.
Yeah. Okay, so what I was going to say then, the important part about this diagram commuting that we're going to use later, hopefully if we get there, is the fact that these squares commute. Or in other words, the components of the chain map commute with the differentiation operator. Is essentially intuitively what this diagram commuting means. So that's going to be important to us later. So,
Yeah.
just for some terminology, he says Fn is called the term of degree n of the chain map. So, definition, all complexes and chain maps form a category, so comp category of complexes.
So we saw an example of a chain map in the last chapter
Right.
in the induced map of the continuous map from X to Y induced had the induced homomorphism from the homology of X to the homology of Y, right?
Right, and
That's just that's like a specific example of what you're doing. It's not.
right, yeah. But we are going to use that to define our functor from top into the category of complexes. So I think at this point I can probably erase this stuff. It's all pretty basic definitions, so get rid of this. Right, so we're actually going to use the induced map to define the functor I was mentioning. So
The object is complexes and chain maps, or
the objects of the category are the complexes. The morphisms are chain maps between complexes.
Okay. Good.
So is it good? Is it okay if I erase this?
Oh yeah, that's fine.
Okay.
Yeah. Bill's doing some independent study category theory.
Did you actually move the camera over here though?
I did, yeah.
Oh, okay.
I moved
Just
it
making
back
sure.
because I thought you were moving.
And Bill's doing some independent study of category theory, and he was working with a student yesterday. He was complaining about looking at functions of functions of functions. It's like everything is a function of functions of functions of functions of functions
Oh
of.
man.
It's not that bad for us today. Okay, anyway, go on.
Yeah. All right. So let's see. Oops. Keep dropping stuff.
Oh, excuse me.
So
Chew some gum or something.
he doesn't give a. Oh, I should cut that off. It's sort of weird. He doesn't actually give a bold-faced definition here, but in these paragraphs here on page 88, he defines functor S star from topological spaces into category of complexes. And so essentially this just takes a topological space. So it takes X and maps it to the singular complex of the topological space on objects. And then on morphisms, takes F and maps it to the induced map. And so actually it's interesting, if you remember earlier when he introduced this notation, he's like, oh, you really should put n because there's one for each level of simplex. Here this notation actually makes a lot more sense because this is a map on the entire complex. So I thought that was interesting. So then he also defines this functor Hn from complexes to abelian groups just by setting Hn of some complex to be its, well, we already defined this, just to be its, you know, entomology group. Right? So wherever we define that, we just have to find how it maps morphisms. Let's see, how do they do that? Okay, so they just define Hn of f is the mapping from the class of Zn to the class of Fn. Zn. So essentially the same thing we did before, and that's well defined for the same reasons. So he doesn't really go into much detail there, essentially because we're just making use of what we did in the last chapter. We're just defining them on complexes now. So moving on to this next theorem here. Theorem 5.2. For each n in the integers functor Hn from complexes to a billion roots is additive. That is if f and g are homomorphisms from one complex to another, then, well, you could have guessed by it being additive. I mean, this is essentially the same definition as in linear algebra, so I didn't really need to write this, but it works well with addition. So this will be useful for us when we do diagram chasing, which we may or may not get to today. So they say proof, a routine exercise, but unlike what I was telling you earlier, Dr. Cook, this time it really is a routine exercise. So I might as well just give it for you. If you recall, Hn of f was defined by mapping Hn of f of the sum over m sub sigma, sigma, just by linear combination on each of the singular simplexes. Right?
Okay.
So if we look at Hn of f plus g, by definition, that's going to be m sub sigma f plus g composed with sigma. And we know that addition of functions splits over composition. We also know that we can split up summations, so this is equal to sum m sub sigma let's write it like this, f sigma plus m sub sigma g sigma, so then that's sum m sigma f sigma plus sum m sigma g sigma, which is Hn of f plus Hn of g.
So what's comp again? Comp is
the category of complexes and
So are we
chain maps.
So are we necessarily looking at like simplexes?
No, these don't have to be simplexes.
Okay.
But the singular complex that we looked at in chapter 4 is a complex.
Right. So what is sigma in this case?
Oh, good point.
Daniel's asking the same question I'm asking.
I may have, I guess I just did this for singular complex then instead of for all complexes. Let's see, how do we define the induced map for all complexes then?
Let's see here.
It's with the class of Fn of Zn. That's what you wrote over there, right?
So basically,
Oh,
I
yeah.
think you end up using
Yeah.
just the additivity of the
class
of like the Fn and the Gn.
and the corresponding additivity of the class, there has
Yeah,
to be
yeah.
an additivity of the class, like the class Cn maps to
Yeah,
class
this
Fn.
here.
So,
He talks about how like
Hn of
you have the
F plus G.
so this, if you had F plus G, it would map the class of Fn plus Gn of Z, but
which you can.
that would be equal to class Fn Z.
Yeah,
plus
so I guess we
class
need to-
Gn Z.
To this of Zn is going to be equal to the class of
So that's like
F plus
and then-
Gn, I guess?
And then you have some boundaries. Yeah, like the
Of
boundary.
Zn,
yeah, which is just going to be Fn plus Gn.
right.
Class of Fn.
So the class,
So basically, what you have to do
Fn
is
plus
to prove that the class of Fn plus Gn is
Gn.
equal to the class of Fn plus the class of Gn plus a boundary term.
right.
Oh, yeah. I mean, he says it in one of the
Oh.
paragraphs. So
Sorry, if I could read.
Yeah, I think we've already shown that. So this is class of Fn of Zn plus class Gn of Zn.
that's kind of like how it's defined.
So you're saying the proof is the proof is not a routine exercise. The proof is a definition.
I mean, this proof is a routine exercise. The proof that F plus G and is Fn plus Gn is definition.
Oh.
Yeah, there you
Yeah.
Very good.
Okay, yeah, I had written that down in the margins of my notes, but I wrote the particular definition for
go.
the singular complex instead of the general definition. So, this next page here,
You can erase that. What's under
Yeah.
the pen?
so this next page here, let's see, the remark he says, it's important that the reader feel as comfortable with a complex as with an abelian group. He says they have very similar structure. So essentially here, this next page or so, he goes and defines all these operations on complexes. So here, let's see, what time is it? I guess when we end 3:15, was it? Or 3:30?
Oh, 3:30.
Okay.
We can even go with 3:40 today because I'm just giving a test and I already have it printed.
Okay.
So the fun is ready for them. So this intuition, right?
Right.
You take the topological space, you trade it for the chain complex.
Right.
Now that's a topological step, is what they're saying. I mean,
Yeah, I mean,
Like,
they're
you-
getting it from the topology.
okay, so I guess they're labeling the step by its. Well, the step. I mean, it seems to me that step is both. I mean, it's confusing to me because it seems like
Yeah.
that step is both topological and algebraic. I mean, that's the bridge between topology and algebra, and then to me,
Yeah.
the comp to ab, that's all algebra. It's just like one kind of algebra versus another kind of algebra. But I guess it's just potato. I don't know.
Yeah.
I was a little bit confused by this statement. You know, that the one's a topological step and the next one's an algebraic one. I guess it's. I mean, fine. The one that just involves algebra. The other one involves algebra and topology. But the middle step is necessarily algebraic. It's like topology, algebra, and then algebra.
Right. Yeah.
Sorry, I mean, shut up. I'm saying uninteresting things.
So, let's see here.
I'm going to develop a subcomplex if I don't stop. Sorry. It's gonna be a long day.
So, I guess I should define. I'll go ahead and define subcomplex and quotient because we're going to be using those later. The other ones I don't think we used in this chapter, so I'll just read them. So, subcomplex. It's pretty much what it sounds like. We say.
So you have subgroups. So those I's are inclusions.
Right, yeah. Yeah, they give you 3 ways to characterize it here. First way, each of the terms is a subgroup.
At least he's using I's
Together.
instead of Yodas. I hate those stupid Yodas.
That's true.
Yodas are so annoying. I just want to put a dot on them. I can't stand it. You know? Put a dot on it already. Just make it an I. I is for inclusion. Or make it a J, because that symbol looks like a J, you know?
So,
Wait a minute, no.
yeah, Sn prime,
No, no, it works.
subgroup of Sn for all n. And then each of your differentiation maps.
Nathan, this is very enjoyable. I think I'm going to let you do the rest of the talks this semester.
Please no. At least not till after October 29th. So, I don't know why he draws that restriction so big. Should be like, yeah. So, all of the terms of the complex are subgroups of the other one,
Mm-hmm.
and the nth differentiation operator is just the restriction of the other nth differentiation operator to
So
the
your
subterm.
so your comment again would be like it's like the inclusions and the differentiation maps commute in the natural way.
Right,
basically,
so
right?
that's their other description of it. They say that another way of characterizing this is this diagram commutes.
So next up is the quotient complex, eh?
No. You're a monster.
What? I'll get up there and put dots in them myself. Star Wars fan.
Okay. So it's like Yoda.
I don't know.
That's where you're coming from.
It's a sad place I'm coming from, but as Trump supporters, gotta take what we can get.
Alright, so quotient. Essentially, you just have.
But I bet Trump knows who the leader of North Korea is. He's at least got
Who
that.
doesn't?
Johnson. I mean, I can understand not knowing Aleppo, but not knowing who the president of North Korea is.
When was this? I didn't hear about this.
That was the next news cycle. It's a recent news cycle.
Okay. Huh.
He's largely disinterested in geopolitics. I mean, which is understandable. That's kind of the point of his political philosophy, right?
See, I stopped checking my Facebook page recently because inevitably someone will post something really stupid and inspire me to write this long, 5-paragraph response.
Uh-huh.
And I just don't have time when I should be studying for the
Very
GRE.
good. That is very good. You should not be distracted by professors and students trying to drag you into unnecessary political discussions.
Yes. Okay, so
That being said.
if you have S star prime is a subcomplex of S star, then we just have to define the quotient
So we're talking, of course,
term-wise, essentially.
and we're talking about abelian groups, so quotients make sense because all subgroups are normal.
Right.
So the factor groups are
Good point.
well-defined. Or
So
well-defined if you're not
Sn,
from that part of the world.
Sn prime, Sn minus 1, Sn minus 1 prime. And then defining the mappings.
Right.
Let's see what he does. He defines
It should just be the partial composed
This
with
by
the
mapping.
natural map.
So he defines partial n, Sn, It's Sn minus 1 prime. Okay, right. Because this is the coset for Sn prime. So he just does it on representatives. He says it's well defined because since
So he actually wrote the formula for that thing. Goodness gracious. I would have thought he wrote this in terms of compositions of the natural map for the quotient and the original differential or something.
yeah.
Surprising.
So kernel and image are essentially the same thing. You just do it component wise. Let's see. Sequence of complexes and chain maps is exact for exactly the same reason that a sequence of Boolean groups would be exact. Namely, I guess I'll write this one out because this is also important. So, exactness. If you have a chain of complexes, or they say sequence of complexes, sequence so A. They're using Q here for some reason. I don't know why he doesn't just put N. He just want to be different, I guess. Also did the superscript. I guess so you don't confuse them with
The ends
groups.
among, yeah.
I guess it's like reserve notation, like you and your usage for dimension over the summer.
I forgot what I did this summer.
You don't remember the dimension thing?
The dimension thing.
And your reserve notation for n? You didn't like n
Oh.
to be used for anything other
That's
than
right,
dimension?
that was insist that n is the dimension of the algebra. And Nathan wants to use n as like a natural index for other stuff. I'm like, no, n is the dimension of the algebra. Like, it doesn't have to be fixed. I'm like, fine.
Right, so this is exact. I guess,
You should make me use like a fracture n for the dimension of the algebra or something awful.
so it's exact if
Unfortunately,
the
I can't draw that
image
thing.
of the chain map, Q plus 1's chain map, is the kernel of the Qth chain map for all Q natural numbers. So then
okay,
short
so-
exact sequence is just one of these guys.
So it's like all possible triples are exact, basically, right?
Right. Exactly.
Given your initial definition of exact, yeah.
So then if this is exact, this is short exact
Right.
sequence. So they also define intersection and sum and direct sum. Those are all component-wise.
Not going to draw the window?
The window.
The top of page 9.
Oh, yeah. I will not draw that. That'd take too much time. Maybe I'll show it to the camera. I don't know, maybe this Violet's copy it, but yeah, so essentially this picture just emphasizes the fact that, on this page here, each one of these are themselves a complex. So if you want to, you can visualize that by having the complexes go
Okay.
vertically. So you kind of get this
Yeah,
lattice.
that lattice picture becomes important for certain arguments later on.
Certain diagram chasing arguments.
Yeah.
So direct sum, intersection, and sum are all component-wise like before. He also mentions in these next few paragraphs, especially towards at the beginning of page 91, I guess one of the more important things he says here.
See, it's interesting. I was reading in his algebra book. He's he's no longer a fan of the sum notation for direct sum.
Oh yeah.
He now prefers circle plus with a lambda under it.
Huh.
So like he's grown out of this in his more recent writing. But anyway, we're where we are. So
I don't know how I feel about it.
that's just notation.
So at the end of page 91 here, he essentially just says that, I guess I should write, if x, the union of x sub lambda, so this is the path components of x, then you can write the complex as the direct sum of the complex of its path components. But I think that pretty much just comes from extending chapter 4 to the definitions of our complexes. So I won't go into the details there. This next set of exercises is interesting. He essentially just goes through and has you prove things like the first isomorphism theorem for complexes,
Cool.
things like that. So it really is very similar to just dealing with abelian groups. It's just got more pointy things. So this next definition is interesting.
You know, with a little bit of build-up, I could assign these to abstract.
So if f and g I probably should erase some stuff first. But if f and g are chain maps, then
Some of what you're writing is like covered by the
that
shelf.
there.
Yeah. So
I should probably. Let's erase this.
So you're defining chain homotopy right now?
Yeah. So, definition, got f and g.
Sequence of homomorphisms.
Chain maps are homotopic.
Oh.
Yeah, you just noticed it, right?
This is just like we did last time.
It's lemma 4.21.
No.
So, if there is a sequence
Of course, the difference being that the derivative maps before were specific to the homology, and
right, this is, I mean, this is just a
general
definition,
complexes.
yeah, this
but the
is
properties of this definition are going to be built off those theorems we did.
right. I mean, when you get right down to it, the arguments we made weren't so much about triangles as they were about the fact that d squared is 0, the additivity, just the general connection of the objects.
Right. So the sequence here, like I was saying, is exactly like the setup we had for lemma 4.21. See if I can find it here. Assume f and g from x, y are continuous maps, and that there are homomorphisms Pn from Sn of x to S sub n plus 1 of y, with the map induced by f minus the map induced by g equal to partial Pn plus Pn partial n, or Pn minus 1 partial n. And the lemma is then for all n greater than or equal to 0, the induced map of f is equal to the induced map of g. So this next theorem here three says 1 F G are chain maps with F. They just use the regular homotopy symbol for this. Homotopic to G. And for all n, the induced maps are the same. And 2, if F is a chain equivalence, which I glossed over by not defining here, but you essentially use the same definition as regular homotopy equivalence, just for chain homotopy. Then Hn of F is an isomorphism. So the proof of this, well, so I guess I was thinking they literally just used lemma 4.21.
No.
But essentially it's just analogous to that proof.
Right.
It's not exactly the same.
Exactly.
But we use the same structure and you essentially just do the same thing.
Proof by pattern matching. Very good.
Yes.
Hey,
And
it's legit.
part 2, you know, essentially this is the same thing we did. I don't remember, maybe this was even in chapter 3, but when we proved that if you have a homotopy equivalence, that the induced map is an isomorphism. Essentially, same idea. So we have this analogous definition of homotopy now. So our next definition is the analog of
Abstract in the cone.
a null homotopic map.
Hmm.
So contracting homotopy.
He says this is the abstraction of the cone construction. Yeah.
Wait, does
Well,
he say that?
He says it recalls the cone construction, I guess, but I'm just reading.
Does he actually? Where does he
I'm
say
reading
that?
between lines.
Right over the definition.
It says the next definition recalls the cone construction of theorem 4.19.
Oh, okay. Huh. Yeah, because actually I read in the margins there, you know, is this related to the cone construction? I guess I just didn't read the line right above it.
Well, that's a good
Because
question.
I'm blind.
Well, that's
because they
but
use they use the C sub n notation.
You know, that's a very good question. We'll restart your device outside active hours. Select this message chain hour. Stupid Windows 10, I tell you what.
Okay,
Sorry.
so
Sorry, Nathan.
of a complex S star is a sequence of homomorphisms C.
I'm gonna start using.
CN.
I'm gonna go to start using
SN.
Linux pretty soon. I've just about had it.
I'll help you install it. Such that
Unfortunately for my work, I have to deal with a lot of Word documents sent to me.
for all n element z, partial n plus 1 cn plus cn plus 1 or minus 1 partial n is equal to the identity on Sn. So I hope the camera can get it there though,
Yeah,
right?
it should be fine.
Yeah.
Okay. So essentially, it's just a chain homotopy between the identity map and the zero map on the complex. So then we get this nice corollary. It's corollary 5.4. If a complex has a contracting homotopy,
Oh,
then-
wait,
Yeah, you can bring it back to me.
Nice light. Oh, by the way, there is a light switch in there. It makes it a whole lot brighter when you turn the other light on.
Oh,
You
yeah?
just thought the lights were on. That's a safety light, so I can't turn one of them off.
Oh, I like.
So
I
feel
like,
free to use the light switch. And
I like your solution. You know, working with the access and control people. It's a very sophisticated
Thank you.
solution. I enjoyed it.
I have defeated. Well, you know what happened this weekend? This lab room turns red on the weekend,
Uh-huh.
and of course, the setup guy couldn't get in. So I'm not because apparently his.
You know, he could have broke the window.
Hmm?
You could just break the window.
I was thinking about that, but.
Ironically, there's some guy stealing stuff from cars in my neighborhood last night. When I got in my car this morning, I'm like, why's my glove box open? But I don't think there's anything to steal in my car. So he might have took the cigarettes that my brother-in-law left in the glove department like 5 years ago. I gotta check that when I get back.
That might.
You know, when I go to smoke. What am I saying? I vape, of course. I mean, come on. I have arguments with Ginny
So
about vaping.
this- Oh yeah.
Yeah, I'm for it. Let's see here.
So they say if 1 is the identity on S, so identity on S, and of course they use 0. 0 also is the 0 complex, which I don't think they explicitly mention anywhere, but that's just this guy. So, by theorem 5.3, part 1, I guess, because contracting homotopy is a chain homotopy between the identity and the 0 map, we get hn of 1 is equal to hn of 0 for all n. So then, because hn is a functor, it has to send the identity to the identity.
Mm-hmm.
So, since the identity is equal to the 0 map, right, because this has to be 0, the only way that'd be possible would be if hn of the complex itself is equal to 0. So, alright, now we get into the fun part.
I like his his little footnote here. This method of proof is called diagram chasing. It's a really simple technique, for each step is essentially dictated, and so one proceeds without having to make any decision. It's kind of like getting past the primaries in a presidential election. You know,
Alright.
it's
Yeah, so this next proof here is
it's fun to try to get Nathan to talk about, you know, principled
Politics.
libertarian stand or something. But I should stop. I'm really a very bad student if you think about it, you know? I think professors make the worst students.
I would put you in detention.
Put me in detention. You know, I don't think I ever went to detention, but it's mostly because I was homeschooled.
School West detention.
Hmm.
Huh, that's true.
My professor, when I took Algebraic Topology, Dr. Latta, he actually brought in the movie where the snake lemma is proved. He hauled in a TV VCR cart back in the day, and we watched the 2 minutes of the movie where the snake lemma is actually proved, and it's actually proved with the details and the diagram chasing in the context of some obscure movie, which I could not tell you. I'm sure you could Google it and find out, but
I actually have watched that before.
yeah, not surprised.
Yeah, so actually it's weird. I don't know, maybe you know a bit about the context here. This lemma 5.5 we're about to get into It's not the snake lemma that
No.
I've seen, but I guess it's somehow related.
It's got the snake lemma's got like 5 things in it or something, right? I mean,
Like this diagram here. If you have like
it looks kind of.
kernel Sn prime, kernel Sn, kernel Sn prime prime up here,
Uh-huh.
and then you got the co-kernel down here. Then they said the connecting map is like, that's where you get the snake.
Oh.
But here they also call this DN map the connecting map.
Hmm.
But it's
I know,
kind of
I have
got
to-
the same diagram at its basis. So.
I'd have to dig through my notes to tell you. But,
They actually don't mention the snake lemma at all
yeah.
in this book, so.
Hmm.
But whatever it is, for us it's lemma 5.5. So.
I'll allow it.
5.5. Maybe it's snake lemma light or something. So.
Subject to the Constitution and bylaws of my office, I will allow it.
As long as I don't start talking about psychology.
That is the first rule of Dr. Cook's office.
Yeah, so this is really where the primes start to get annoying, but if I don't use his notation, I'll screw something up, so I should probably use his notation.
Well, actually, it's not entirely true. You can talk about psychology if you criticize it. If you want to say psychology is a waste of time, or something like that, I would allow that.
So this is a short exact sequence of complexes. So I'm just going to say sequence of complexes. Well, I guess exact sequence. Then for each n,
See, prime.
there's a homomorphism. Dn from hn of s prime prime to hn minus 1 of s star prime, given by mapping the class of Zn prime prime to class of I sub n minus 1 inverse of p sub n inverse of c sub n prime prime.
So the inverse.
There's the boundary between the inverse.
Oh, good catch. Thank you. Boundary. Yes, nth boundary.
So being that that's a short exact sequence, that means that the I map is injective.
Right.
So the inverse
Yeah, that's a good observation.
exists at least with domain the image or no the.
Right. Yeah.
Yeah.
So we have to show that
But you're feeding it
the image of this nth differentiation map is contained in the image of I
right.
in order for it to work. So that's part of the proof we're going to be doing here.
Yeah.
But one of the other confusing things that it doesn't really reference, which makes it really hard to follow until you realize it.
Mm-hmm.
How do we know that this map has an inverse? It actually... I mean, he doesn't show that. Essentially, I believe what he's doing here, this is just any section of Pn inverse, I suppose.
Yeah, because it talks about lifting.
Right, and he also he uses lifting in a very general sense. Like, I don't know, maybe I'm missing something, but it seems to me
So
that
we
it's different from what we did back in chapter 3
have-
when we talked about lifting.
We have surjectivity of P
Yeah.
by the exactness of the sequence, but well, there's another 0 beyond what you wrote. That's a far right.
Good point.
Yeah.
Thank you. But I think essentially